talk about goes back, well, over at least a decade. So an awful lot of people have contributed to it. I've tried to put up the name of the main people on this slide, which includes a few people in this room. But there are a lot of other people who contributed to this work. I've been leading the Autonomy and Verification group for about a year and a half now, but the group itself has roots back into a logic and computation group at the University of Liverpool, which, again, there's decades of work behind that. So what is an autonomous system? So I'm quite a public understanding work in schools, and when I'm talking to 6-year-olds, I say an autonomous system is something that is controlled by a computer and has to make decisions for itself. So I dodged the whole question of what does autonomy mean by saying it makes decisions. And so far, no 6-year-old has asked me what I mean by makes decisions. Because obviously, your computational systems make a decision at some kind. But we have a kind of intuitive sense that these are sort of more significant decisions. Often I'm looking at autonomous systems that are embodied in some way. And if it weren't for driverless cars, I'd say I was looking at robotic systems, but people don't think driverless cars are robots. But here's some examples of the sort of things we could look at. There are unmanned aircraft. These are spacecraft, Mars rovers. This is a search and rescue robot. This is a home care help robot. And this is a Lego robot that I was in school. And they all make decisions at some level. I hasten to add, I haven't worked personally on all of these. But they're examples of the kind of thing we tend to be thinking about when we're talking on autonomous systems. So sort of a key feature here is that they are out there in the real world. They're getting information in the real world. They are taking actions that have some kind of impact on the real world. So there's a kind of inherent unpredictability there. And also, they're not simply, this is where we get to the kind of what is a decision. They're not doing something simple like just wandering around with some obstacle avoidance behavior, but at some point they make some much sort of clearer choices that they're going to do a particular thing. So when we are sort of building these, I mean, there's quite a lot of architectures you can use for these systems. We tend to use an architecture like this. We have a cognitive agent. I will go into more detail about what one of those is. But the cognitive agent is the one that is taking the things that we think of as the interesting decisions. And that is where we focus our verification effort. We often have what we choose to call autonomy support, which are a whole load of other technologies, lots coming out of artificial intelligence. So there are things like planners, path planners, schedulers, localization and mapping systems. So these are all, quite smart pieces of software and quite complex pieces of software, but they are assisting this decision-making approach. We also have sensing systems. When we started this work, we used to say, well, everyone knows how sensors work. They're long, well-understood technology, but now there's a whole kind of generation of smart sensors coming up, which again have a lot more computation inside them. So there's kind of more of a question about how are they actually functioning. And similarly, we have dynamic control systems, which ultimately connect to our actuators. And they're often using sort of differential equation-based feedback control systems in order to control motion or action waves. So what is a cognitive agent? Here is a whirlwind tour through terminology. So an agent is generally defined as something that can be viewed as perceiving its environment through sensors and acting on that environment through effectors. So that's a very, very general definition. I think the key thing is that the agent is embedded in something else. It's not a self-contained system. There is some outside the agent loop going on, and it's doing sensing, and then it's doing act. A rational agent is one that does the right thing, which is a great definition. For a long time, I used to describe the agent we had as a rational agent, but actually the terminology lots of terminology about rational agent has gone into game theory. And so if you hear of things which like maximizing the reward or maximizing their utility, a lot of that is wrapped into this concept of a rational agent now. So the idea that they do the right thing is that they have some kind of mechanism for deciding what the right thing to do is, and lots of game theorists or people who are adjacent to game theory consider that to be some kind of game theoretic action. So a cognitive agent must have that's desperate. Must have reasons for making the choices it does and should be able to explain them if necessary. Such agents are programmed and analysed by describing their motivations, which you might call goals, desires, or intentions, and information, their knowledge and belief, and how these change over time. So again, there are lots of undefined words there. I think the key thing, particularly that we get into a variety of cognitive agents, which is the beliefs, desires, intentions paradigm, and that's very much explicitly defined by this bit here. When you're programming a beliefs, desires, intentions agent, you are working with kind of first-class constructs in your program, what the goals of the agent are at any time, which are things it wants to bring about in the world, and what its beliefs were. You represent those explicitly. And obviously, the intuition here is that potentially you can then go back and why the agent chose to do something can be explained in terms of those goals and beliefs. In fact, there is comparatively little work in actually generating explanations from these programs. But in theory, it shouldn't be as difficult as with some of these other programs. So what a typical beliefs, desires, intentions agent has is something called a reasoning cycle. This is one in the Gwendolyn language, which is what we use for most of our work. I'm actually going to start at stage E. So what happens is it gets perception and messages in from the outside world, and it processes them. And it turns all of these into something called an intention. It contains a set, though in most applications this is a queue of intentions. So each one of these things, if it's a difference, if it's a new piece of information, sharp off as an intention, though there's kind of nothing associated with that. It's just, this is something I need to handle and do something about. In stage A, we select one of those intentions to be the current intention. If it's a queue, it's at the top of the queue. Or we sleep the agent. If there's no intentions at all at that stage, we sleep the agent, and the agent does nothing until it actually gets an alert that there's something changed in the environment. Are there any unsuspended, non-empty intentions? So that's an intention which you can actually do something with rather than one you want to do some cleanup on. If there aren't any, you go back and see if anything new is happening. Then find all plans applicable to the current intention. And plans are the things that the programmers supply. So plans are a set of things the programmer has written how you want to deal with certain things that may be happening. And you have a whole set of these. So you've now got a whole load of intentions. You've got a current intention. You go away and look and see what plans you've got that might handle the current intention. You pick one of those plans and apply it. And what this does, in fact, is extend the intention out into a kind of stack-like structure of a list of things you need to do in order to handle that intention. Is it empty? Because if it isn't, don't bother doing it, go back. If it isn't, you pop the top thing off the intention and you do whatever that thing is, and then you go round. So because intentions are not in a queue, this means if you've got multiple intentions with plans in them going at once, you're interleaving what's happening with all of those. So you're doing the top thing on one intention, then you go to the next one, do the top thing on that, go to the next one, do the top thing on that. At some point, some more information came in, you get a whole lot more intentions, you get, so it can get potentially quite complicated with multiple intentions being handled at once. Just so you can have a look at, so the idea behind these beliefs, design, conventions, programming languages is that they are levering sort of folk psychology about how decisions are made. So this is in a kind of pretend syntax to make it a bit clearer. I'll show you some real syntax in a minute. So these are some plans. The top one, the thing at the start, plus G empty. The plus means you acquired a goal, and empty to have your hands or grippers empty. And so that bit at the start of the plan is a trigger event. So that is something that's happened that you need to react to. Then the bit in the curly brackets is a guard. So you might have lots of different ways of handling any event, and the guard helps you decide which of these are applicable. So this one says you believe that you are holding a block. So you've got a goal to have empty grippers, and you currently believe that you're holding a block. And the action you're going to do is send a message to a coworker asking them to take this block off you. And as you can see, that within these kind of goals and beliefs, we're using, first order predicate logic syntax. Well, yeah, first order. This one is more or less the same, but we borrow syntax from Prolog. So where we have the capital letter A, that is a variable. So we're saying here, if you want to have empty grippers and you believe you're holding something, could be anything, that's A, and then it unifies with the A over here. So send a message to your coworker to take whatever this thing is off them. So that's a slightly more general plan than that first one. That lets you handle a whole variety of things you might be holding. This one is sending messages. This one's a similar thing. You've got a goal to be holding a block. You believe your grippers are empty. You can see a block on the ground. And this is an action in the world, pick up block. And that goes outside the agent bit of the program to one of your dynamic control systems, which has the code for picking up a particular thing in front. So yeah, there's significant stuff happening here, but it's not in the agent. And yeah, this one is just you can also have negations here. So that's, and you're not, if you believe there's a block on the ground and you're not holding the block. And then here, the action here is, well, get a goal to hold the block. So you can sort of chain these things and chunk up the code in ways that may or may not make sense. So the idea is that this is very declarative, that once you're familiar enough with the syntax, you should be able to look at one of these pieces of code and say, oh, I can see what that's doing. Yes, that's the correct. That's correct. Or not. There is a lot you can do with programming language design and clever constructs and stuff to hide or remove complexity from solving problems. But fundamentally, if you've got a complicated problem, your solution is likely to be complicated. Sometimes complexity just bites you. There's a lot you can do to try and get rid of that. So, what's happening here? So this is, I'm going to talk about this program later. This is a program for satellites flying in formation and handling. So they have to move to a formation, and there's some errors that can occur in their thruster systems that they may or may not have to fix. And this is literally the code that we ended up with. And this was after doing several verifications. The verification failed. You realize there's that case you've not handled. You have to add another plan into the code. This is simply the code for maintaining your position once you've got into formation. So the top one says, if I'm trying to achieve, so this exclamation mark is the actual syntax of goal. So if I've got a goal which says I'm trying to maintain a position, and I believe I'm at that position, and I believe I'm currently supposed to be assuming a formation, and I haven't aborted for some reason, and none of my thrusters are broken, then I just I activate this underlying control system, which is now just maintain yourself in this position in the formation. I get rid of this. I add a belief that I am now maintaining my position, and in the underlying system, that makes the goal go away. So you've now discharged this goal, and then I do some cleanup, which I haven't even shown you that code. That's another whole bit of code, but it's deleting a whole load of beliefs you no longer need and deleting some goals you no longer need and that kind of thing. The next one is, okay, so I'm trying to do this, but I don't yet believe I'm in position. Then I need to get a goal to get to position, and I'll go and do this. And once I've got to position, then I can maintain my path. The next one says, I'm trying to maintain position, but I've aborted for some reason. At this point, and I believe that my thruster's broken. So at this point, I'm just going to wait until the thruster's fixed and then see what's going on. So that star construct is just suspend this attention, don't do anything with it, like to a side of the queue, wait until you now believe that the thruster's been fixed. And when that happens, carry on. And because these is an achieved goal, it never goes away. So once it's completed that plan, if it's not maintaining its position, it will go away and look for another plan that it can now find. If you're trying to maintain a position, you don't believe you're assuming a formation, just delete this goal. It's irrelevant, it's hanging around for some reason. And similarly, if you think you're trying to maintain a position and you've aborted for some reason, then delete that goal. So there's a whole load of kind of craft in there, which makes it much harder to understand what's going on. But it's all about handling edge cases which popped up during the verification, that sometimes things have got a bit out of sync with each other, and you're still trying to maintain a position, but actually you've aborted, or you've been told you're no longer trying to get and this is hard to read. I mean, I wouldn't like to claim that this is a nice, clear, declarative piece of code where it's obvious just by looking at it that it's correct and it's covered. So that's why you need to actually do some verification of these things. As I say, we use the Gwendolyn programming language, which is a VDI language and interpreter implemented in Java. It has a variant customized for use with autonomous systems. And that's things like this: wait for something to become true. There's just kind of things that tend to crop up if you're actually in a body system. You have to kind of waiting for things to happen. And it integrates that verification technology. It's named after Gwendolyn up in the little corner. I gave a talk at the PhD symposium yesterday. One of the things I forgot to say was never, ever invent your own programming language. Having said that, moving swiftly on. This is what we do when we try and verify one of these things. So this bit inside the dotted line is our cognitive agent. So exceptions are coming in. And they are things like, I believe there's a block on the ground, I believe I am in position. And so we actually have something here that's taking the data from the sensors and abstracting it into these predicates, which are at the level we want to deal with them. Because your sensors don't say, you're in position now. They say, here's my estimate of where we are, and then something has to decide that. We're close enough to wherever you want it to be. We have perception, and what we do when we're verifying, so we just verify this bit, so we're not verifying these bits up here. So again, this is the bit that's going out the commands to pick things up or move somewhere. What we do is we say, well, what are all the perceptions coming in that we are interested in? And we verify using model checking, which if anyone here is not familiar with it, just think of it as exhaustive testing, purposes of this talk. We verify over all combinations of what can happen. If we have here is like a really super simple piece of code that's supposed to, if you believe there's an obstacle, then stop. If you believe there is a path, then follow it. Those are my two plans. So the perceptions we're interested in that come in could be, is there an obstacle or is there a path? So in this case, the things we check, what does it do if there's no obstacle and no path? What do we do if there's an obstacle and a path? What do we do if there's no obstacle and a path? And what do we do if there is both an obstacle? So that's all the combinations of things that could come in. And for instance, we might have a property. So here's a property. If the agent believes there's an obstacle, then it will try to stop. And we say try to stop because we don't actually know for certain what's going to happen there. And obviously the correctness of this property depends on the order in which those two plans get selected in this bottom case where there's both an obstacle and a path. So essentially, that's what you end up checking. Have you got the ordering or the selection mechanism on this plan? And obviously, often when there's several things that you could do, it starts doing something, and then another combination of things come in, so it can get quite broad. But we verify that. So. And we do this using a tool called Java Pathfinder, and this was developed by NASA, and it's a model checker for Java bytecode. So unlike most model checking technologies you may come across, where we take the agent program, we model it in the modeling language of the model checker, and then we verify that. In this one, we run the program in a Java virtual machine that has backtracking capabilities. So we actually model check the actual Java bytecode that is executed in the interpreter of the and then we have an automaton that is watching all that backtracking behavior and sometimes pruning it. And that automaton is a fairly standard Buki automaton expressing a linear temporal logic property. I don't know how much gory detail you want about how we do this. You have a property specification language. On the bottom row, we've got all the standard linear temporal logic kind of constructs. So there's or and not, until and release, which we don't use very often. We more often use the diamond means which eventually something will happen, and the square, which means always this thing happens. But we also have sort of at the propositional level. So these don't, the Fs can't have temporal properties in them. So the propositional level we have, the agent believes something, the agent has a goal, the A is the agent is taking an action, I is the agent has an intention, ID is the agent intends to do that. Technical details I won't bore you. P means something's perceptible in the environment. So it's not really about the agent, but sometimes it's useful to have that. And very quickly, Java Pathfinder itself runs in Java. So you've got two Java virtual machines going on here. You've got the Java virtual machine that Java Pathfinder is running in, and then you've got the Java virtual machine that it is running where it can do backtracking. So we have our automaton that's checking the property running in the native virtual machine. And when it gets one of these things where is there a goal, does the agent have a belief, then there are kind of hooks within Java Pathfinder that let you go into this automaton and lets you look at values in fields. So what we do when this is running is that every time the agent gets a belief or a goal or something, in that object, it updates a field and says this is true or this is false. Which means when you set this up, you have to say, from the property, you're checking which ones you're interested in. So those things are actually hanging around to have a true or false value. So that's what it does. It then looks through at this point and sees if that field has been set. It's very boring. So here's an early example that we did. These were the satellites I was talking about in that was code. And this was some work we did with some control engineers, I think they would describe themselves as. They were originally in Southampton and then they moved to Sheffield. So they did this kind of nice simulation. They did two simulations. One of the satellites is, well, they're spacecraft when they're exploring the asteroid field. They're satellites when they're orbiting. So they did a kind of nice simulation for us. So we could run these things in simulation. They also had some physical sort of mock-up satellites which could move around on a table, and they could hit them with a broom to knock them off course. And then you could see if they were kind of correct. So we had this program in Gwendolyn, which I'm not going to show you because I've already shown you a fragment, and I don't think you gain anything from seeing the whole thing. But broadly speaking, if you got instruction to move into some specific position in a formation, it would activate some underlying path planning procedures the control engineers had developed. Once it had a path to move in position, it would move into that position, and then it would try and maintain that position. While it was doing any of these things, one of its thrusters broke. There were a couple of things it could do. The thrusters could break either because a fuel line break and they had backup redundant fuel lines, so it would switch the fuel line, and it could detect that because of the pressures on the fuel line, or they could get something called a short across the grid. So that's an electrical fault, which could be fixed by switching it off and switching it back on again. So you detect what kind of fault it is, and you take the appropriate action. After you've done the verification for a bit, you discovered, well, there's bits in the verification where you run out of redundant fuel lines, which is why we had to put that abort thing in. So there is a point where I don't know how to fix this, and I can have the board send some kind of message saying something is wrong with my thrusters. So one of the properties we proved here is this one here. So I've said if this says if the planning process succeeds, then either the agent eventually believes it's maintaining its position or it believes it has a broken thruster. These aren't actually things which were in the property specification language. I'm just trying to make this a bit more readable. So each of these is actually one of those expressions up above. So the top one, which says planning has succeeded, then that is if the agent requests a plan to get to some position, then eventually it believes it receives the plan. So that's, saying, assuming this underlying path planning thing that it's doing the right thing. So there you can see in the proper specification in non-inclusion law, it's always the case that the agent has sent a query saying it wants to get close to position P, and then eventually believe that it has a plan. And you'll notice that plan has just been instantiated with the word plan. I mean, the actual running code, these plans came back with kind of numbers and identifiers, but in the verification just said plan. I'll get onto that in a minute. And this one where it's the plan eventually, planning execution, if the agent executes one of these plans, then eventually it will believe it has reached the desired position. And that's because if you remember when I showed you the verification process, all these things that come in, we explore all combinations. So there are paths through this verification where you ask for a plan and you never get one. There are paths through the tree where you execute the plan but you never get into position. And so these are kind of saying, assuming everything else in the system is working correctly, then eventually we have this one. Anyway, Kubernetes has 16,609 states and takes 1 hour, 20 minutes to prove. Now, anyone here has any experience, model checkers will be horrified by the combination of these two numbers. No way should 16,609 states take longer than a few seconds to prove. We are executing Java bytecode to transition between states. We have essentially the entirety of Java as our modeling language. So what we're counting as a state is a much higher level of abstraction, and there is a lot more work done. I don't think that necessarily explains everything. So a group at Delft wrote a bespoke model checker for their BDI programming language, which was a lot more efficient than this. I had a bit of a rant yesterday about people publishing work that doesn't necessarily cover everything. And you can no longer get hold of this model checker. The code isn't open source, you can't run it. I don't know quite how much of their language it actually covered. Any Gwendolyn program you can put into the system and model check. So there's a lot of complexity in there. Were you?
But these are states in the Java Pathfinder, so these are symbolic states.
Yeah.
They contain variables.
Yeah.
So that's not too surprising that you can't compare this to the numbers that you get with spin or whatever.
Yeah, no, it's super different. And when I have a mechanism for exporting these things out to spin, and it's like when I export them out, so I'm discovering what the program model looks like here. I'm generating it on the fly. When I export that out to spin, I explicitly say the entirety of all the states in the program at once and the transitions between them. I don't know if that explains. I mean, having now dug into this a bit, I think this is slower than I'd like, but I don't think it's disastrously slow. But when I show it to model checking people, they're like, why are you pursuing this tool? Okay, so I mentioned that a little bit, but I said plan. Just kind of how we do this bit where we say, when we're doing the verification, where we say, all these predicates are coming in and we want to explore them around order. So what we do is we write a Java class. So this all goes into the model checker because it all goes down to the bytecode. And when we get to that get perceptions thing, we call a method in our environment called get perceps. And when we're running the code on an actual system, then obviously that may connect to external sensors or it may do something like that. We write a special class when we're doing the verification, which does this kind of random generation. So here you can see, this is a bit of code for a cruise control, and the beliefs we're interested in are, have you actually started doing anything yet? And are you at the speed limit? And you can see up there we have a Boolean. We just randomly generate true or false for at speed limit. And we add that to the beliefs that go in if it's true, if it's not. And then we randomly generate what was started. And again, we add that. So you can get the 4 possible combinations of these two beliefs. And that goes down into the underlying Java pathfinder. And what Java pathfinder does is when it comes across a random, it branches the search space. So that automatically branches the search space. We don't actually use Java's random generator for this almost entirely because that lets me add some hooks in, which make it easier to debug and trace paths through. So what we find, obviously, is we get, in even moderately simple programs, massive state space exposure. So you have to do things at this level to start reducing that. So we started putting things in here, which were things like, in the case of cruise control, the driver will never press the brake and accelerator pedal at the same time. Just remove all those states where both of these things are true. And we did a bit of stuff saying, well, you need to document all these assumptions that you've made. But then someone came to visit us who later came to work with us, who does runtime verification. I've got to say, yes, in the actual system, we had this thing. I said there's this thing that abstracts the data, so we call it an abstraction engine. But that's a discrete piece of code, so you can analyze that and see exactly what it's outputting and sending to you. So this is what we do with runtime monitoring. So in this double dotted box here, you've got, here's our cognitive agent, and here's the special verification environment we've written with whatever assumptions we are making about the behavior of the environment to try and control systems. So this is where we do our static verification around those two things. When we're running the actual system, we're running this block here. So we still have our cognitive agent. We have this abstraction engine that's taking sensor data and turning it into our inputs. We may have an actual Java environment. It's more likely we have some kind of thin Java interface, which is connecting via sockets or something like that to some simulator or some sensors on an actual robot or something. What we do is we have a trace expression. The trace expression is in the language of a runtime monitor, and it talks about what are acceptable sequences of things you can observe. We write a trace expression which explains what our assumptions are about the environment. So the trace expression says, for instance, I assume the driver will never press brake and accelerate at the same time. I assume I will never be at the speed limit if I haven't accelerated first. That thing. From that, we automatically generate the verification environment. So the verification environment now embodies the trace expression, but we also generate a runtime monitor that can watch this connection between the abstraction and reasoning engine. So it can look at the beliefs that are being sent in and the actions that are coming out. And if they violate one of these assumptions, so the driver presses brake and accelerate at the same time, then it will throw an exception. I mean, of course, there's now a whole major question, what would you do when it throws an exception? If you're in some kind of testing environment, then hopefully you've got a whole load of safety features anyway, and you suddenly get, your assumptions about when you did your verification were wrong, go away, do something else. If you're in the actual deployment environment, then you're going to have to start talking about, fail-safe modes, what happens when suddenly you're operating outside as per your verified envelope. Yes, what about all those other bits? So I had this thing. So you have all these, very sophisticated systems in here. And, this code in these systems as well. So we sort of got to the point where it's all very well saying, we verified the cognitive agent. And when we started out, we had a bit of a story where the cognitive agent is the bit that's new, it's different, it's the scary, autonomous, making decisions things. We've been handling all these other things for decades. We know how to create safe systems that have these components in. But that's sort of practically not really the case. So our first attempt at sort of dealing with these was a vehicle platooning example. So platoon is where you have mine's wrong though. A queue of vehicles. The front vehicle is being driven by a human driver, So this is a simplified version of the autonomous car problem. And the idea is that you join a platoon, you join somewhere in this queue, you switch over to autonomous control, and then all the vehicle has to do is follow the vehicle in front of it at a safe distance. So lots of the decisions being made by the driver. And what you have are protocols for joining and leaving these platoons. So although there's a driver in the front vehicle, there's also a software agent there. And so, car wants to join, it sends a message to the platoon saying, hey, I want to join, and I want to join this position. Assuming the leader of the platoon thinks this is okay, a message gets sent to two cars in the platoon to widen their spacing. So now the vehicle, at the point that spacing is wide enough, then a message gets sent to the car to join, at which point it can change lane and join. You can try verifying these protocols. And you can have, in our case, an agent that enacts those protocols. So theoretically, it could be the agent you verify could be the one that was actually doing this. Obviously, around this, you've got all the communications that are going between the vehicles, and you've got the actual dynamic control systems in the vehicles. So the idea we had was we'll do a normal thing with the agent. We'll verify that it reacts appropriately to kind of incoming messages. And then we will verify the timed behavior of these other systems, because there's a certain amount of everything happens in a reasonable space of time that you want to capture here. And the idea was that the agent we could verify in our normal way. So we abstract away from all these timed automaton, and we explore all the sequences of messages they might be sending to you, but without any timing bits. And then when we're doing the timed automaton, we have a simplified model of the agent, which ignores all these esoteric edge cases about what if you get a message saying you can join the platoon when you haven't even requested it in the first place, kind of type stuff. And so we can then create, verify the timing behavior of those. We did a bit of proof to show that the kind of over approximations we were using meant that you could just combine the results. You've got these three systems and they'd still be true. So if you've got something's true of this, and with the agent approximation, then it will be true with the actual agent. And so you can join them all together with a big and. So this is a property. If a vehicle never believes it has received confirmation from the leader, then it never initiates joining the platoon. That's the bit we verified with the agent. And if an agent ever receives a joint agreement from the leader, then the preceding agent has increased its space to the front agent. So that basically means that the agent is never going to start trying to enter the platoon unless the space has been created for it. This is the actual property. So here you can see in the AJPF property specification language. So you've got this first bit because it won't even try and do anything unless it's got a goal to be joining the platoon. If the vehicle has a goal to be joining the platoon, then it's not the case that the vehicle will perform a changing lane maneuver. And this is that release construct. But you can think of it as until it receives a joining agreement from the leader. So that's that first property. And then here's the UPAL timed automaton property. It's always the case that if A3 is the leader, A3 is the joining agent, is ready to change lane, and the leader knows that a vehicle is joining, then A2, which is the one we want to move, has increased its spacing and it's finished. I'll put my name. It's a nice paper, so I'm hoping you are a little suspicious of this. It's true, but we've got two different logics here. Is this telling us actually anything meaningful? Would you trust? Yeah, because here I'm talking about vehicle. Here I'm talking about A3. You have to trust that these are the same entity. Here I've got, ready to change lane. You have to believe that's the same as changing lane 1. So, I think it was a really nice step, and it was a really nice kind of way to kind of say, well, we can do this, but there are but there obviously is some shortcuts. So the next thing we tried, or are trying perhaps, with something around concept of contracts and assume guarantee. So this is a high-level view of a system for a search and rescue agent. It's getting information in from sensors. In particular, it's got a heat sensor. So you imagine it's searching for people in the rubble of some collapsed building. So it's getting up heat signatures of different intensities. It has a goal reasoner, that's a cognitive agent, and that's actually trying to decide what the priority is amongst all these heat signatures, where it should go next. It's got a planning agent, which is a path planning system, and that's, once it's picked one of these places to go, it will generate a number of candidate routes that you might take to that heat signature. The plan execution agent then picks one of those routes, and the plan execution agent is looking also at a battery monitor. So it's trying to make sure that it always has enough power left at the end of executing one of these plans to get back to its charging point. If it doesn't, if it can't find a plan that it can do within the battery allowance, then it'll send a recharge signal back to the goal reasoner and say, can you send me a new goal to be where the charging point is? And otherwise, it sends this out to some execution. It goes off, it goes to that position. So what we did, because we've had several different logics here, so I don't want to subvert them, but the idea is each of these has a contract, and it provides a guarantee it will do certain things under certain assumptions. And we write these all normally in advance. So that means we can say, if we can provide bits of code that meet those assumptions and guarantees, then the whole system will have some property. So this is just an example of a property. If at any point all plans sent to the plan execution agent by the planner module are longer than the available battery power, then eventually the current plan will contain the charging positions, the goal, or there is no route to the charging position. I don't think people want me to talk through this kind of thing, but you can see there's a bit here where you've got all the plans in the plan set, and the length of lead, or for all those plans, length of lead is greater than the current battery power minus T is your estimate how much battery you will use for that plan. This just means that the plan execution agent has actually received this information. This GP means that the planner has met its guarantee. Then eventually, G is the goal. So G will be your charging position, and it will be in your current plan, or alternatively, the plan set be empty. There's no route. So this is just to show what we did in the Gwendolyn for the goal reasoning agent. So the Gwendolyn, the guarantee this one was if first bit says if current goal, that's G, is at the charging position, and then this GH pair are the information you're getting for extra position and the heat sensor. So GH that's the heat signature at the current goal. It's in the goal set, and all the other goals in the goal set have a lower heat signature. So always picking up the goal with a high heat signature. And the other part of the guarantee is if you've had this read charge signal, then the goal is going to be the charging position. So those are the kind of two cases. So we actually did two properties in Gwendolyn. This one is the second one. If you believe that you need to do a recharge and you believe you're currently supposed to be generating a goal, which was the kind of extra detail we needed to add it in there, then eventually you will pick the goal as position 1-1, which has to be the charging position. And this is one of the limitations you get when you do model checking often, that your finite state, so you can't take arbitrary charging position. So we said the charging position is 1-1. And then you say, and obviously this means it's always. Sometimes you maybe do more than just one check, but there's a kind of fundamental limitation sometimes. And down here, we're doing something similar. We happen to know that location 3-4 is where we have the highest signature. So we're checking that in that particular situation, that's and we actually did a few variants. And so we still got this kind of mismatch that I showed you with the last thing. But now at least the mismatch is explicitly saying, have I done the proofs here that allow me to state with reasonable confidence that I'm meeting the contract? And I'm not sure it feels cleaner than to just smoosh all these things together. It makes it clearer where the gaps might be, and makes it clearer if you're writing something like a safety case where you need to provide some justification or evidence that what you have done is actually what was required for verifying this part of the system. So we've got a variety of examples. Matt, any day now, is going to tell me we have a paper ready for submission.
No pressure then.
with an example where we've used a whole variety of different things. We've used AJPF, which is the system we use for Gwendolyn programs. We've used Event B. I used Event B in that last example for the planner. Daphne is a kind of Floyd Hawes style programming environment with proof support, pencil and paper. This is me doing a pencil and paper proof that a radiation sensor will output the right value. And even simulation. So we had a localization and mapping component in the system, and we had this simulation of a radiation storage room, and what I did was make the agent. So we just wanted to check that it goes to the right place, right? This is you're supposed to be going to a certain position, we'll go there. And we just ran that, generated a whole load of random positions and looked at how close it got to those random positions. And so there were whole loads of different evidence you might supply based on what you can actually reasonably do with the component. But some of this was just kind of what other techniques can we use? So that's kind of a whirlwind tour. We've done lots of other stuff like machine ethics. Happy to talk about machine ethics. We have a book which hopefully CFP will okay the moment I send them an email, but I update the captions onto the figures. So that's coming out at Cambridge soon. Also, all the stuff, so it's called the Model Checking Agent Programming Languages Framework. You can find it links to the GitHub, plus the key papers at this URL. I have a slide with tiny references on it, but Carlo said that if I send him the slides or a link to the slide, he'll put a link on the webpage, so you don't need to quickly memorize all of these. If you're interested, you can go and have a look on the iFM. Thank you very much.